Here we are. Welcome back. How you doing? I'm Agent Ultra, and on this stream I hack on stuff in Haskell and I build things, games, libraries, so on and so forth. And sometimes I learn things like this algorithm that we've been working on for a while. I'm learning about how to implement wave function collapse. This is a project we took a little break from for the past couple of weeks, but we're back on it. Wave function collapse, if you don't know, is an algorithm generally used for procedurally generating textures. It could generate a whole lot of other things, such as procedural algorithms are wanted to do. However, we're going to be mostly using it for textures, I think, just to try it out and learn it and see how it works. It's one of those dragons I've been trying to slay for a long time, because it's used in a lot of games and a lot of cool applications, and thought, why not? Let's try it out in Haskell. See what we can learn. So that's what we've been doing. That's what we're doing. We have a ton of code right now, built off mostly from interpreting this wonderful tutorial made by somebody who is not me, that I've been learning from. So it's a bit of gridbugs. Org wave function collapse. This blog from the fine Stephen Sherritt, who lives in Sydney. What's up, Stephen? And yeah. So this isn't the only way to implement it, but this is the way Stephen implemented it in Rust. We're learning how to do it in Haskell, see if we can figure out how it works. And then maybe compare with some of the early attempts that I've made at trying to implement parts of this on my own, and come to a better understanding of what's going on here. Maybe there's a different way we could do it still, and maybe a more functional way. But yeah, let's see if we can make this work. Last I checked, let's get the test builder running, and we'll see if we can pick up where we left off. So we're going to stack test fast, while watch, and get going there. I think, if I'm not mistaken, that we're somewhere near the bottom of the algorithm. Somewhere near elimination. Yeah. The rules should always hold. Yeah. Let me look at the log. Fixing errors, relative frequency, uninitialized enable accounts. The very generically named commit, make progress. Okay, we added is contradiction. And some debug tracing, okay. Right. I think we are getting to a point where the algorithm is unexpectedly eliminating more, like completely eliminating a cell, if I remember correctly, like all the possibilities out of a cell prematurely. Yeah, so we have this trace amps here. I'll check when is contradiction, and then we do some errors here. Okay, and okay, yeah, we are. So we added that. We're hitting it. We tried to propagate from our test example to this cell at 1.4. the pattern index 1, and I guess at this date it doesn't exist. Wow, it's a lot of 03 action going on in 03 here. As I'm scrolling up and down. Oh, that's sorry, I'm looking at the dimensions. They're all the same dimension, yes, they are, of course. So these are the enabler counts, okay. I'm not sure how much useless data is to me at the moment. Oh. Okay. So we are in the propagate step here. Okay, so this is throwing the error when there's a contradiction in the neighbor cell from the current one we're at. So the neighbors, this means that the neighbor cell we're trying to propagate our change to has nothing left to propagate. There's no enabled patterns. I wonder if we can get the enabler count for that neighbor. Let's see, when enabler count, I'm looking online, it's 6.3 here. When enabler count in the direction is 1, and it doesn't contain 0 counts. So if that's true, and that's right, this would mean that when we get to the contradiction of the neighbor cell here, contradiction I think is checking the actual values of the cells in that neighbor. If there's none activated, that would mean that that would mean the enabler counts disagree with our is contradiction predicate here, I think. And the state of the cell might be in like a weird place. That's probably, how would we test that to make sure that that's true? Well, we could put out the enabler counts and the cells, the cell state, maybe. That's the propagating, that's our current enabler counts. Oh, what's enabler counts? So that's the neighbor cell. Cell pattern enabler counts for the compatible pattern. Okay. So when we get to line 622, we have this trace out here. Before we hit the error, we get propagate enabler counts and this handy dandy little list of coordinates. So it's not possibly not empty. It just might not have the right one that we want to propagate to 1, 4. I don't see 1, 4 in there. Okay, I think the way we can show that for sure though is to actually like bind out this expression here. I'm just going to call it NC for now. Okay, enable the counts is for the whole neighbor cell, perhaps? Oh, okay, so that's not what I want. I'm just going to print enable accounts, which probably silly, but I just want to be sure that we're in this. Okay, accounts. I'll print the cell state. So I print the neighbor cell. And let's sort of lift. Know that. I think we can IO in here, can we? Maybe not. No, we're in a pure place, so we're gonna have to debug trace that out. Okay, that's no problem. Okie dokie. Okay, so that's our enabler count array. Let me just grab all of that and put it into a nicer buffer so for us to poke a stick at. Okay, so this is our cell state. The pattern enabler count is redundant because it's in the cell. Good times. Very large array of them. So our cell possibilities here. False, 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 false. No cell possibilities left to set that cell to or eliminate. That would throw an error. Hey Goku, how's it going? Welcome to the stream. Nice to see you back. How's it hanging, friend? Okay, so yeah, everything being set to false is no good. And in our implementation that we're ripping from here, don't think this should be. Okay. So this code here has some issues, but not bad ones, just misdirections. So this one, I don't think this name actually gets used. For one. That's the only place on the page it's ever listed. And so what we've done in our implementation is for each direction, so there it is, for each direction in the directions that are available, we get the neighbor coordinate of the removal update, the record on our stack that we've pushed. So the removal update will have a coordinate and a pattern to remove. So for each direction that we're going to go in there, I'm going to get that neighbor and the cell of that neighbor from the grid. And then we're going to go over the compatible tiles in the adjacency rules or that tile in the removal update in the direction we're currently looking at. So we get the grid, we get the neighborhood coordinate for that direction, we get the neighbor cell on the grid, and then for the compatible patterns in our adjacency rules and the pattern index for that remove pattern in that direction. Yeah, we get a compatible pattern. Get the enabler counts from the neighbor cell. Enabler counts from the neighbor cell for that compatible tile. Or compatible pattern in our nomenclature. Then we have this if condition here guarding us, saying that if direction, if they name, there's only one. Otherwise we decrement it. Well, we decrement in any case. But if it is of 1, and we're about to decrement it, then if there is a 0 count in another direction, the potential tile has been removed. And we want to avoid removing it again. Okay, so this is looking at the enabler counts that we've pulled out. Here from the neighbor. So that's the neighbor's count. So if the neighbor contains any 0 counts, it is enabler counts. And we remove the tile from the neighbor cell's possibilities. Here it looks like we've got that condition where we collapse them together into one expression. So instead of having if and then if, we're just going if this and this. That could be not right, actually. We remove the pattern from cell. We're on this line. let's try moving that down in. I'll grab you here, pop you there. Pop you there. I mean, no, I think that doesn't change anything. Doesn't change the meaning of the program very much because this whole is bracketed on it as well, and there's nothing after it. The only thing this code is doing between here and here is nothing. I think that's probably why it was ANDed together. Because then we do all of these things. In that case. In here. Here. Update the entropy heat. The neighbor cells, entropy. Hey Twitch D, how's it going? Yes, the collapse is back. Somebody on the YouTube side of things was asking about it. They seemed really sad that I hadn't updated in a while, so thought I'd get back to it. So this then produces the entropy heap. Here, add entropy cell. So assuming this function does everything just with the heat, doesn't touch anything else, that's fine. We can push this one here. And then finally, tile removals. We push a new removal update with a compatible tile and the neighbor cell. So there's another typo there. Pretty sure that doesn't show up anywhere else either, actually. No. So yes, Twitch D, it's a general algorithm for in the class of procedural generation algorithms, usually for texture generation. People have also used wave function collapse for other things, but that's the primary one that's been used for. So for like game maps, textures, things like that. Just trying to learn about the algorithm itself. And I did pick up a copy of that algorithm design in Haskell book, and I've been working my way through that in order to better understand algorithm design in Haskell, like the book said. Which, for reasons, is quite different than algorithm design in like most texts that I find anyway. Like I have that big, huge algorithms book that almost every university course doles out, but it's all procedural code. And in the art of computer programming, for reasons, all procedural. Except for like the specifications of the algorithms, I guess, but which are given in maths. But yeah, so algorithm design in Haskell, I think it's an interesting book. I think it's sufficiently different. There's a sufficiently different approach you can take, which leads to some interesting results. And I've always been kind of mystified a little bit by it. Like how the actual process of like how to do it and how to design them. So I'm learning lots by reading that, by doing this, and that sort of stuff. So maybe there would be a more functional way of representing this in Haskell that'll be like a lot easier to express than this has been. Trying to mimic this Rust code. Anyhoozles, tile removals. I gotta push those on, so there we go. Removal pattern, the compatible patterns remove, and the neighbor forward, essentially. So this will push the pattern we're looking at removing onto the stack for later removal on the neighbor's cell. And this actually does the removal. The neighbor cord. Maybe that's what's causing the problem here in this algorithm. Because this actually calls neighbor cell remove tile the compatible tile. So I'm assuming this mutates the neighbor cell somehow. And if we then push on a removal update onto the stack with that compatible tile index and that neighbor's coordinate, this algorithm is going to come back around, pop that off the stack, and is going to go through all this and remove it from the neighbors. It's going to kind of like remove it again. Yeah, sure, Twitch. No problem. I think it has a bug in it. I'm starting to think that maybe it has a bug in it. Because if this pushes the same compatible tile we just removed from here back onto the stack for the same neighbor coordinate, eventually this counter should get down to 0, I guess? And then we stop removing it? Like that seems to be, yeah. I don't know, change my mind. You know, chat, like, do you see what I'm talking about here? So we push, I don't know, remove pattern index 4 at this coordinate on the stack, right? Pop that off. For each direction, we get the neighbors here. So we call propagate. Maybe I'm misunderstanding this part here. Self simple core state. But what I think is happening with this code is that while there's still removals on the stack, we pop it off. And so we have a pattern index 4 on there. And if we initialize this stack, there's initialize the stack. Here. With the initial remove updates, tile index and coordinate. Tile index here is for each tile index in all of our possible tiles, patterns. So if the tile index is not the one that we just collapsed to, now this in Rust, this star possible, that's a mutable assignment, right? And so this is initializing the stack, at least, to those tiles, pattern indexes, that are the ones we haven't collapsed this cell to, and the coordinate is going to be our coordinate, the one that we collapsed. Okay. So in that case, when we go to propagate, this will be this removal update. The coordinate in the removal update is the cell we collapsed. That's why we have to get the neighbor's direction out. Okay. And so, okay, so never mind. I'm understanding this better now. So this now will push the coordinate of the neighbor on in order to propagate the change there. And then we do this here. So then we remove that from that neighbor cell. Okay. I still feel like there might be a bit of a loop here, but I think that works better. So I'm going to double check our initialization code, make sure that's right, and follows the example algorithm here. So when we collapse, we use collapse at. In our version here, our pattern stack, our stack of pattern removals, is built from mapping the removed pattern over the impossible patterns. We take the cell index, which is our cell, the ones that we just collapsed to. So that part's right. Impossible patterns. Takes the array, filters out, keeps only the ones that are false. It gives us the pattern indexes. I guess that was meant to be like the ones that can't be picked here anymore. Which is not quite the same, I don't think, as this one here. Which is all the other ones other than the one we picked. So yeah, still in the set of possible ones that you can pick. The ones that are not the ones we collapsed, the pattern index we collapsed to. So I think that's different. That might be the source of our troubles, possibly. Okay, so we have impossible patterns. Did I write possible patterns? I did. Okay, so why don't we just filter on possible patterns? Filter where it's equal to the pattern we're trying to collapse to. Okay, so collapsed cell. Well, I don't have that like value in scope here, which I need. Collapsed cell updates the state. So we do the pick pattern here. And they do it a little bit above. Okay, so we could probably do the same thing too. Oh, but we get a reference to collapsed cell, which will have just pattern index there, but I think it'd be nicer to pull that up. I have a feeling. Just pass it in. Oh, hold on. Just like that, and then we filter for pattern where it's equal to pattern X. Okay, so that will keep all of the ones in the possible patterns as equal to the ones we just collapsed to. I think is what this one isn't doing here. The removal updates, as long as the tile index is correct, which is cell index here, which chord tile index. So tile index comes to possibles. In this code, not pattern index. Yeah, that's right. Sorry, I think chord is the one I was meaning to look at. Chord comes from, yeah. So it's this coordinate. Yeah, I'm discovering that Twitch. It's not the greatest. It's blog code, that's for sure. There's some unused names that are bound but not used. There's typos and stuff like that, so beware. Okay, so I think that's correct, because our cell X is also our parameter here. Yes, and a lot of very, like, procedural initialization of data and such. But what I liked about the blog post more than the code was the explanation. Some of those parts are pretty cool. Especially near the beginning. Where we're talking about the overlapping tile stuff. This part is probably the best explanation I've seen of it. Whereas a lot of other algorithms that try to explain the overlapped tiling method kind of rush through it and don't really give those nice little graphics that kind of explain that you only use the top left pixel from the patterns when you're collapsing things down into the output grid and all that sort of stuff. And like even generating the adjacency rules and like how those work. So yeah. I'm hoping maybe at the end, the tail end of this, I'll come out and finish that part of the book that I'm interested in and finish this implementation, and then we'll be ready to do like, okay, here's how we would do it in Haskell, really. Because I look at some of those, like I read ahead a little bit in that algorithm design book, and dang, it's cool. But one of the common patterns that it uses throughout is this idea that, like, really locking in the whole thinking and reasoning in terms of equations and manipulating equations. And so right off the bat, like one of the most important manipulations it gives you, one of the most important rules, they call it, maybe you might call it a theorem or something like that, is the fusion law. And they use it quite a bit throughout. So I don't know if I can pull up a sample. I have a sample of it. But, like this example, this algorithm would probably fit closest to like somewhere in dynamic or exhaustive search. But I don't think they give you, well, the basics probably in like the intro. But yeah, like it often, like a lot of the algorithms start off with like a very high level description of what it should be, and then break it down using like the fusion law, for example, to get to an efficient implementation, or at least a good enough one. Yeah, so like re-implementing it in from scratch. Yeah, exactly. So I tried that a bit at the beginning of this whole Odyssey. Couldn't get it to work. So that's why then I was like, oh, okay, let's try it in Rust. Try following the Rust code more closely and seeing where we went wrong, or where I went wrong there with it. But now I'm finding, yeah, like just translating from Rust to Haskell is like part of the problem, perhaps. But we're so close. Like it's there. Maybe there'll be some insights at the end of all of this that'll be interesting. Who knows? So there's that at least. Wait a second. That was it. That one little fix. If anything, though, it has, like, doing it in Haskell has made me read the Rust code a lot more closely. So there's that. You know, at first when I was reading the blog post, I was like, oh, yeah, okay, yeah. But now I'm like, oh, actually, like, typo. Oh, unused variable. Oh, okay, like, this could be, you know, that kind of stuff. Anyways, it's working. It was initializing the stack properly. We were doing it wrong. Now the test passes. So, I guess, like, the test is a good, at least shows me that this is, from end to end, all of the pieces we've built in this work for a tiny example. I guess we'll clean this up, get rid of the debug statements, and then we should set out on a mission to create a little demo app with this to view such a texture and see if it looks similar to the pictures, the nice little pictures we've seen on our blog, on the blog post we've been working from. And then kind of review everything. And then figure out. Yeah, well, when the code is good, I would do that for sure. Part of the experiment too, like when I first set out to do this, was to like start off with a poor, like slow implementation but correct, and then do the fast version, which we haven't gotten to because we got so mired in just getting it to work at all. So hopefully that'll be possible now as well. Okay, so let's get to the cleanup part. Get rid of our debug stuff. Okay, we don't need that. Through that. That. Over here. I'll leave that in for now. The error. Okay. Most of the major type errors are gone. I saw some warnings in there. Okay, the tests. Test. Okay, so in the test stuff, there's a couple of build warnings. That's not so bad. Test spec. Don't think we even need debug in here. Clean those up too while we're at it. Why not? Did I enable this anywhere else? Borrow that from. Did. Probably there too. If it's commented out, it doesn't exist. Yeah, okay. That probably cleans up enough of them. I know there's one in here that I should just add to my ignore list. Oh. Got overly ambitious. Silly me. Going too fast, not paying attention to what I was pacing. There we go. Yeah, that one. Okay, cool. Woo! Let's do it. Stage. Commit. Fixed it. Okay. Wait, how are we gonna do our test app now? Do I have an executable set up for this to build? Probably. Executables, yeah. But, okay. Call it wave, function, collapse. We'll just call it WFC test. Yeah, probably like an SDL app or something like that. I have to get a load of this lib nonsense. There. Just that. Go into main. That. Let's do LAN. Test. Okie dokie. So, let's maybe do an SDL app, because that's, unless there's an easier graphics library for Haskell. There are some interesting ones. Oh, what am I thinking of? There's one I'm thinking of. Maybe it's on this, loaded on this page. Gloss. Okay, the vector graphics is not going to be quite as useful for what I'm thinking we need here. We need something raster. Twitch, that's a good question. Lots, really. People have used it to generate poetry, 3D models. The Wikipedia page, I think, has quite a few. Or no, the original page does. So anywhere, like, any kind of structure where you have self-similar patterns, like, and so the self-similarity is very localized. Right, so, like, these are texture examples, because that's, like, the canonical, like, I guess, original use. There are some other implementations. So it generates levels in Bad North and Caves of Cud, Dead Static Drive, Town Scraper, and a bunch of other video games and prototypes. Yeah, I've heard of people using it in like other, like text generation even. And like there's a lot of tutorials out there in a more that cover a more simple version of it, where it doesn't do like the overlapping tile version. Like the more simpler one is to just have the adjacency rules listed out explicitly. And for that, like there's a lot of like tile layout type stuff, tile maps, 3D scenery, stuff like that. Alright, so anyway, you need to generate that kind of content from like a simple kind of example, can extrapolate out and build larger versions of it. That looks similar. There's an interactive version even. Runs in the browser. Let's see if it crashes my system. With the Unity runtime. Oh boy. Oh, okay. That's a neat little tool. So I guess you pick a bunch of these to kind of create a basic idea, and then you can solve the rest. I don't know. Something like that. There's a wave function, yeah, like, because it's almost like a fold, right? If there's like a span for it or something. Maybe. So yeah, quite a few use cases. It's just a neat algorithm. I just always thought it was kind of cool. Always wanted to be able to implement it. So um, yeah, and like maybe in like some future game I make, it'll be in there. I'll use it. It'll be nice. Nice to have. Just nice to learn. Okay, so yeah, I think that I was thinking of gloss, but that's of a vector library. So we'll have to just go with SDL, yeah. I think SDL GFX as well in order to create texture maps that we can render. Oh no, that's some base SDL too, maybe actually. Oh yeah, video.renderer, yeah. Copy point. You draw points. It's a vector geometry, so I think all we'll probably need for it is to like get a texture, draw points on it. Surfaces are the old school ones. Yeah, maybe we go drop down even to surface here, and that would let us manipulate the raw pixel data, convert that to a texture, and then we can just render that with the renderer. Something like that. Okay, well, let's get that set up. Get a window going. I think this machine, this VM already has SDL2 on the path just from prior dev stuff we've done on the stream with SDL2. Alright, so while that's going, let's just get our basic setup code going. Initialize all. Yep, sounds good. Doesn't really need to initialize all, but we're just going to do it anyway because I'm lazy. And this is just a prototype demo. Yeah, let's create a window. Create a renderer. Enter our main application loop, sure. And then destroy the window. Cool. Yes. All good, I like it. Oh, that's the full examples right here. Ah, okay, better. Kadoosh. Just gotta go over that. Clean that up. Boom. Okay, well, while that's waiting to compile, why don't we hop over to Reddit, see what the Haskell community is up to today. A Munihack Wasm experiment. Convert Haskell expressions to point-free in your browser. Cool. Cool. Okay. At least got some minor WASM support in the browser for Haskell now. Maybe they had to write some of it by hand, though. I've tried, like, the WASM compiler backend has been in GHC for a while now. And it works great for server-side WASM, like running in WASM time, but I was trying to get it run in the browser and I couldn't get it to go, well, to actually, like, interact with the DOM and stuff like that. Couldn't get that to work. I think maybe it didn't even work at all. I can't remember, but it's been a while ago. Well, that's cool. Awesome. Water sort in Haskell. Troubles with kind and gadgets and type families. Oof. I feel you. I was thinking of that library we were working with last week for the RSS feed stuff, and I'm not against its use of types. It could use better documentation, but it uses an open type family to make it extensible. And I think that's actually a pretty smart move on their part. And that's why it exists the way it does. Dependent types in Haskell, part 4. How to properly lift IO. Some people looking to help some help here. Ah, a Haskell command line tool, Swiss Army knife, got released. Cool. Alright, good for you, friend. Neat. State of the Haskell on the web front end. What's it like? We were just talking about this. Well, it kind of does, yeah. Okay, so like this is mostly GHCJS type stuff. Miso, I think, is a framework for that. Although, what's this? Wasm Miso examples. The GHC Wasm backend supports the JSFFI feature, allowing Haskell Wasm apps to interact with JavaScript seamlessly in the browser. What? Maybe I gotta try this again. I mean, things move fast. The repo contains a few examples to demonstrate this ability, all of which based on the Miso frontend framework, using an unofficial port, as well as an experimental JS-ATL WASM library under the hood. Are you kidding me? What? Oh, okay, I do have to revisit this. This is awesome. If this is actually Haskell running in WASM, this is fantastic and good news. There's a project that I haven't done because this wasn't working that I really want to do. And it might be able to be... It might be viable now. Oh, that's great. I'm going to star that and get back to that later. That's so cool. Now, you've been able to do that with Miso directly, using like some very specialized tooling to do that, but if we could do that with straight out of GHC now, that is super cool. Because then I can, yeah. I'm not going to talk about it, but it's cool. It's a cool project, I think. Fun to do. But it really needs to be able to run a front end in the browser with Canvas and stuff. This is cool. A dictionary of single letter variable names. I thought this was a fun little website. So in Haskell, we often use single letter variable names, especially in the type level. And it makes a whole lot of sense when you get used to it, but it can be a little bit daunting at first. Because there's a lot of convention around like Y, A, and B, and M, and that sort of thing. But if you follow the conventions, your code will be readable, more readable to people who understand them, and likewise, you'll be able to understand the code other people are writing a little bit better. And so this page just gives explanations to the conventions. Just writes it out. Right, M as a type. This one, not so much, but monad for sure. Like sometimes you'll see monoid M, I do not doubt. But oftentimes it means monad. Ooh, even term level ones too. Oh, okay. Term level conventions I don't really see that much, and I don't really use. At the term level, I usually write out like the full name. P and Q, profunctor value, bifunctors. All big scary sounding words, but when you get used to Haskell and you learn what they are, you're like, oh, it's actually not as big of a deal as I thought it would be. Although, profunctors can be a bit of a what? Okay, so we got a compile done, but it's not going here. Okay, we need linear in our package. Linear. I'm gonna order this a little nicer here. Okay, we're building, we're good. Okay, can we run it? We can. Hooray. Q, I think it was. Yeah, okay, cool. All right, so now what do we need? We need the input for our algorithm to run it, all right, which is going to be a bitmap of some kind as our test. Where's the seal from? Maybe from here. I don't know if I want to implement like a whole file selector widget thing, so maybe we'll make it like a command line thing. In which case, it's a little op parse duplicative. Yeah. Let's consider that image. Although, not that literal image, but an image like it. Okay, op parse applicative is a nice little library, if you haven't seen it before, for Haskell, to parse command line options. Mm-hmm. Something like that? No, I don't want arrows, just applicative. Yeah. Ah, this ties in nicely to something I was discussing a little bit on the Fediverse earlier today. I was talking about applicative do. I haven't really used it a whole lot. I'm not a huge fan of do notation in general. I use it a lot on the stream because we use monads quite a bit, where it would be kind of annoying to not use it. So, like, I'm not against it. I don't hate it. But it's just, yeah, I don't like to use it as much because it ends up with like code like we have in wave function collapse. It's like very procedural looking and kind of very nested and vertical. And sometimes it's better than the right thing. But at the same time, it's not about, do notation isn't about like imperativeness or sequentialness or anything like that. Because you can use do notation in monads that have nothing to do with sequencing at all. Anyways, that's all to say that the applicative do extension lets you use do in more places, and some folks suggested to me that I should give it a spin for that. So we might be able to use it with parse applicative here and see if it makes this code look a little nicer. So first, with options.applicative, we have to bring in, yeah. Let's order this a little better too. Okay, and then our options. Which really is going to be like a file. It's our input file. Image. Maybe we'll make it a file path. it's going to want that to be a new type instead of a data, because it's only got one field. Okay. All right. And then our parser. So we have, we're going to try it out, give it a shot. Language. Applicative do. Do that applicative. So we should be able to just pop do on there and go image. Let's see, stir option. Metavar. Don't really care. Help me. Okay, that should be good enough. And then we can do like this, maybe? We had record wildcards. Yeah. So that works. Do I have a good method or program for taking notes? I've been taking notes in a flat text file, and I wish I could do cross-references, etc. To this, yes, sort of. It's probably not going to be a satisfactory answer, though. First of all, when I'm doing notes, I usually write with pen and paper, generally. But I do sometimes use text files, and it's Emacs. So, for example, this whole file is an org mode file. It's called org mode. It's got this nice little feature where you can like have collapsible sections, and I can switch these from like to do and done. I can add my own custom things. This whole world available in org mode. It's wild how far it goes. Literate programming, agendas and filing and data munging and all kinds of weird stuff you can do with it. It's awesome. But you can do cross-file links too. So for example, in my wave function collapse library, I might want to have like a link here. Sorry, I'm in the Haskell mode here. Org store link. Yeah, so actually cool. I'm just typing it. Okay, so I Control C L there. It says stored. And I can go over to my thing file here. I can slowly Control L that. I've got the link on my insert link menu here. I pop that in, give it a description. And now I've got a link here. And now I can just do Control C, Control O. I can go right over to that file from here. Yeah, I'm an org mode nut. I've published books in it. I have done literate programming in it. I do literate DevOps with it. So one of the things I love using it for is like you can have these code blocks. Like that. I can make it a source block, and like I could have a REST client, a package called REST client in here. And REST client basically, it's like an HTTP REST client, and I can use that to. I don't have that REST client installed here, but like you can write get whatever some API call slash whatever. All right. Given your data, you can have like variables up here, so you can have like API key, whatever. And have that in some protected encrypted file, and then pulled in through Emacs and all this sort of stuff, and it'll give out the results. You can make it formatted in JSON, and you can absorb that JSON with another code block that can then, yeah, it's nuts. And then you can all publish it into a document and build a report for people. And so a lot of times I'll keep a lot of my ops tooling in this kind of format, or I'll have like a file with handy dandy tools and scripts for doing various things to keep stuff together or whatever. And yeah, it's super useful to be able to do that. It does slap. Like, it's unreal. Like, I can't believe it's free and that it's open source. And yeah, I use it so much. It's really kind of cool. Yeah, like integrating with SQL even and your SQL database and being able to pull in queries that generate tables for you that you... And then you can use all of the table processing functions available in Emacs, Lisp, and stuff. It's nuts. Nuts. So, yeah, but I don't usually recommend it because most people don't use Emacs. So, it's kind of like a secret weapon, I guess. Okay, so anyways, this is the applicative do style notation with record wildcards versus what we might have had to write out beforehand, where we'd have like the constructor here and then this functor apply and then apply and apply here. Which, like over and apply and apply. It ultimately, this do notation desugars to this. So I get the... I get it. The thing that gripes me about it, like... And it is useful for reasons, but binding extra names in scope is like... That's the thing that niggles me. Like, I don't want to... I don't need to. I don't want to. But at the same time, I guess it does kind of make it a little bit more readable, I suppose. Although record wildcards kind of obscures like what's happening here. I think it looks very confusing to somebody who's probably fairly new to Haskell. It's not obvious what's happening here, but it does make for less code, I guess. I don't know. Anyways, stick with it. Try it out for a little bit. See what I think. All right, so now we got the parse options. Now we can parse those babies and get our greeting. Okay, greet, bind, exec parser, ops. Info. Oh, and sample is our parser. Okay. I don't know what helper is, but okay. Options. I need to bind. No, it's just an equals. Oh, exec Parker runs it, and oh, okay, then we bind the results, so that brings sample. And parse options. exec. Yeah, exec parser auths. Oh, no, parse auths. What's the problem here? Parse info to parser. Okay, helper. Okay, we gotta do this bad boy here. Info needs more arguments. Two arguments. And the other one is full desk. Okay, like that. And then just put stir, then option. I just print options. Okay, we didn't rebuild. Okay, we need file path. Here. In our package, bang. Right here. Okay, there's our options. So I got missing image argument. Okay. And if we do that with image test.jpg, whatever. There we go. Then it parsed it out and we got the options there. Okie dokie. So then we need to be able to load an image and get the bitmap data out of it. And then we need to take that bitmap data, put it in our texture data to run it in our algorithm. Right. So for that, I think we need SDL image. I think I also have installed on my local VM here. So add it to my package. Maybe not. Oh, maybe not. Okay. Maybe we can find it in this here, so I'll just... I know I should use index environment and stuff like that, but I'm just gonna... We just app search. SDL image. There we go. Live SDL2 -dev. Okay, so SDL image, load is our function, it takes a file path, gets us a surface. Or we can get a texture. Okay, so we can load any PNG, JPG, TIFF, GIF, WebP, Cure, ICO, BMP, PNM, and so on and so forth. Cool. Let's create a little test image. We'll make it pretty small. 12 by 12. Black background. Sounds good. Doesn't have to be super fancy. Sure. Bing. Bing. Use like a olive green in there. Cool. There's our little test image. Maybe we'll put like a little rosy red bead on it there. And some blue petals down here. Okay, there we go. I'm gonna need to put it. Oh, how do I save it so my VM can get it? I don't think it matters too much, actually. Okie doke. Skadoosh. Let's load that surface. I'm gonna make a directory called data, some test data, and let's see, users, me. What's the user on this machine? Desk, top. Oh, I forgot what I called it. Sprite 001. Oops. Have to export that. Call it PNG. Okay, so I think we should be able to load that. There we are. Okay, so then if we do stack exec, and image will be data sprite 0001.png. Cool. Okay, and then we need to load that data. Yeah. load a file path. Gives us an M surface. Okay, so we'll want to pass, I guess. How do we want to do that? Maybe just load it up here. We need another language extension for that. Overloaded record dot. Down. And we'll just pass image in. Okay, now we got surface in there. How do we render it? Just to know that we've loaded the data properly and the library's working and all that. Oh, we got to initialize the library too first. That's right. How do we get an F init flag? A JPG and a PNG. Okay. That's just any foldable F. So maybe like a list. Capitalized. Okay, and we'll qualify this. And initialize as well. That seemed to have mostly worked on that part. So then it's back to rendering in SDL, rendering surfaces. Okay, so we have update Windows surface. Surface blit. Converting surfaces. Applies load BMP right in there. Meh. Yeah, whatever. Can we create a texture for the renderer from a surface? Oh, yep, right there. Create texture from surface. So we'll do the draw color, clear, and then we'll do our update to the renderer here. Although, I don't know if we want to do that conversion every single darn time. On the loop. Yeah, the time of the lap, who cares? We'll do that. Create texture from surface. Because I'm probably going to be getting rid of this code anyway. At least this part. There, renderer, image surface. That's it. We get the image texture, and then ta-da. And then how do I render the texture? Present, yeah, renderer state though. What is it? Render. Raw, present. Okay. So we manipulated with that. Render target. Like that, maybe. Check. Do. That's a maybe there, I think. Renderer, maybe? There we go. Okay. Somewhat compiles, hopefully. Maybe it'll work. Ba-bow, ba-bow. Cool. SDL call failed. Set render target. Okay. SDL exceptions. Well, that's progress. But unfortunately, we're out of time now. So I guess we'll have to call it here. I'll create a commit for this so far. We'll just remove the rendering stuff for now. And leave a little to-do there. There. We'll stage this. Steal all that. Deleted. Yep. Good. Cool. Add WC demo. Suitable. Boom. Push that all up. Hey, Kazrock, thanks for joining in. Nice to see you. But hopefully we'll see you next week. So all the code you've seen on the stream tonight lives up on GitHub. I'm Agent Ultra there as well as here and elsewhere. Under github.com. Wave function collapse. There we go. So there it is. Paste that in chat. Boom. And if you're interested and want to check it out for yourself, there you go. I do these streams once a week, usually on Tuesdays at about 10 after 8 in the Eastern time zone. So if you want to join in, you can write that down in your little calendar. Or if you like to get the notifications, give us a follow here on Twitch. Or if you're on YouTube, give us a subscribe, thumbs up, a like, and all that stuff. Turn your notifications on, you'll get notified when I go online and do these streams. Because sometimes, once in a blue moon, I do sometimes do streams off my normal schedule. But Tuesdays is the main one, so tune in for that one. And hopefully we'll see you next week. You can find me on the Fediverse as well. You can follow me there on the types.pl server at Agent Ultra. It's got links to everything else, like my website, my YouTube channel where I back up the VODs for these streams, and where I post often updates about upcoming things that I'm doing and working on and just making fun of. And also go to the link above my head. That's declarative.tv. That's a little website that showcases other streamers who are doing things in other declarative style programming languages, not just Haskell. They have a Discord link there where you can join the Discord, and there's a channel for this stream where you can talk about your projects, ask questions you didn't want to ask on stream, or if you're tuning in from a different time zone because you're watching the VODs, you can chat with me there as well. So yeah, may your monads always be free and your types always check, and we'll see you next week. Take care and happy hacking.